Hi there everybody, and welcome to lesson 6. In our previous lesson, we looked at the relationship between current, potential difference, and resistance. I showed you how to express that relationship mathematically as V equals I times R, and we did some calculations using that equation. By the end of this lesson, you should be able to solve problems using the equation V equals I times R and calculate the effective resistance of resistors in series. Let's start by solving problems using the equation V equals I times R. The question that we've been given is the following. Calculate the effective resistance of two resistors in series if the current passing through them is 0,16 amperes and the potential difference across them is 4,2 volts. Right, to solve this problem, we start off in exactly the same way. We first of all write down the information that we've been given. We know that the current I is 0,16 amperes. We know that the potential difference V is equal to 4,2 volts. Write down our equation. V is equal to I times R. Let's make R the subject of the formula. Therefore, R is equal to V divided by I. Let's substitute in our values. V is 4,2 volts. I is 0,16 amperes. 4,2 divided by 0,16 will give us an answer of 26,25 ohms. Now that wasn't very difficult, was it? Let's try another one. Calculate the effective resistance of two resistors connected in parallel when the current passing through the main circuit is 0,77 amperes when the potential difference across them is 4,2 volts. Well, first of all, let's write down our information. Our current I is equal to 0,77 amperes. The potential difference V is equal to 4,2 volts. Now we approach this problem in exactly the same way. We write down our main equation, V is equal to I times R. We're looking to calculate effective resistance R, so let's make R the subject of the formula. So R is equal to V divided by I. We substitute in our values. V is equal to 4,2 volts. I is equal to 0,77 amperes. 4,2 divided by 0,77 gives us an answer of 5,45 ohms. Now that you've done those two problems successfully, I want to teach you a further set of tools that will allow you to calculate the effective resistance of resistors in series more efficiently. This circuit has two resistors connected in series, R1, which has a resistance of 10 ohms, and R2, which has a resistance of 12 ohms. What is the effective resistance of this combination of resistors? In other words, what is the resistance of that single resistor which would replace these two resistors and still allow the same current and the same potential difference to be maintained in the circuit? Let us recall what we already know about resistors connected in series. The current remains the same throughout the series circuit. The potential difference divides over the resistors in series, and the potential difference across all the resistors in series is equal to the potential difference across each individual resistor. We're going to use these findings to derive a formula which will allow us to calculate the effective resistance of resistors in series. As we stated in the recap slate, the potential difference divides over the resistors in series. Therefore, V total, the total potential difference, must equal V1 across R1 plus V2 across R2. So V total equals V1 plus V2. Now we know that V is equal to I times R. So let's substitute the values of I times R for V in the above equation. So V total will then be I total times R effective is equal to V1, which will be I1 times R1, plus V2, which is I2 times R2. We know that current is the same through each of these resistors. So we can divide through by current, and we cancel current out, and we can see now that we are left with R effective is equal to R1 plus R2. Can you see that the effective resistance of resistors in series is equal to the sum of the individual resistors in that series circuit? Let us now do some calculations to make sure that you're comfortable with the formula. What is the effective resistance of two resistors in series when R1 is equal to 150 ohms and R2 is equal to 230 ohms? Well, the problem is simple. We write down our information. R1 is 150 ohms. R2 is equal to 230 ohms. Now our formula is that R effective is equal to R1 plus R2. Simply substitute in the values, 150 ohms for R1 plus R2, which is 230 ohms. 150 plus 230 gives us a total of 380 ohms. Now for a calculation that's a little bit more complicated. Two identical light bulbs are connected in series. They carry a current of 5 amperes when a potential difference of 220 volts is applied across the series combination. Determine A, the effective resistance of the series combination, B, the resistance of each light bulb, and C, the potential difference across each light bulb. So let's answer part A, the effective resistance of the series combination. We write down our information that the current is equal to 5 amperes. The potential difference is 220 volts. Therefore, using the equation, R effective is equal to V divided by I. We substitute in our values. V is 220 volts. I is equal to 5 amperes. 220 divided by 5 gives us a value of 44 ohms. And now on to part B, the resistance of each light bulb. To do this calculation, we know a few things. First of all, we know that R1 is equal to R2 because the two light bulbs are identical. We also have a series combination. Therefore, the effective resistance must be equal to R1 plus R2. We calculated the effective resistance in part A as 44 ohms. Therefore, that must be equal to R1 plus R2. If they are identical, then it's equal to 2R. Therefore, R must equal 22 ohms. If they are identical, then R1, which equals R2, equals 22 ohms each. And lastly, the potential difference across each light bulb. Again, because the light bulbs are identical, let's use R1 to calculate that potential difference. We know that the value of R1, we have just calculated in part B, is equal to 22 ohms. The current flowing through R1 is equal to 5 amperes. Therefore, if we use the equation V is equal to I times R, and we can say V1 being the potential difference across R1, substitute in our values, I the current is equal to 5 amperes, R1 is equal to 22 ohms, 5 multiplied by 22 is equal to 110 volts. And therefore, the potential difference across R2, which we'll call V2, is also equal to 110 volts. Our answer to part C reinforces a very important concept about series circuitry. We worked out that the potential difference across R1 was 110 volts. And because R1 was equal to R2, therefore we said that the potential difference across R2 would also be 110 volts. Now we know in series circuits that potential difference is split between the resistors in the combination. Therefore, if we add up the individual potential differences of 110 volts plus 110 volts, that will give us our total of 220 volts, which was the total potential difference of our whole combination. To show you this, have a look at the simple demonstration. We will start with just one light bulb in series, and I will close the switch and observe how brightly it shines. Let's compare this circuit with another circuit which has two identical light bulbs connected in series. Can you see that the single light bulb is glowing brighter than the two light bulbs in series? In the combination of the two identical light bulbs, do you notice that each of them glows with the exact same brightness, yet dimmer than the single bulb? This is because the potential difference is split equally between them. Therefore, each bulb will glow with only half the brightness than compared to the single bulb, as each bulb will only have half the potential difference across them. Can you guess what the effect would be if we connected three light bulbs in series in our circuit? Do you see that the three identical light bulbs in series are glowing very dimly, yet with identical brightness? Again, the total potential difference is split into three equal amounts and distributed evenly between all three light bulbs. Besides our light bulbs glowing more dimly as we increase the number of bulbs in series, what else is important in our circuit that we must take note of? Well, as we increase the number of light bulbs, we are also increasing the resistance of the circuit. And as our resistance increases, so the current in the circuit must decrease. Adding resistors in series has the same effect as increasing the length of the conductor. The longer the conductor, the greater the resistance, the smaller the current. That's all we've got time for today. Please join me for lesson 7. Thank you and goodbye.